from Minsk, and the title of his talk is Joint Talk with Toru Morimoto, Extrinsic Geometry and Linear Differential Equations of SL3 type. Boris, you're welcome, and thank you for agreeing to give a talk here.
Thank you very much. Thank you for the introduction. Just to be clear, in the title, both extrinsic geometry and linear differential equations will be of SL3 type. So it's not just linear differential equations, but also extrinsic geometry. I actually gave a talk on a broader subject, a more general subject related to today's one. I think during the spring semester. And the motivation stays the same. So we'd like to study, we'd like to understand embeddings into projective spaces, or more generally into flag varieties via certain linear systems of partial differential equations. So this will be overdetermined systems of PDEs. Normally they will have finite dimensional solution space. And but today I will not speak about a general theory. So general theory speaks about embeddings of racial homogeneous varieties. I'll just describe one particular example, and which is exactly what we call embeddings of SL3 types. And in some way, this is an attempt to generalize, or to look at to generalize very classical embeddings. So we of course know that classical embeddings of rational homogeneous varieties would include rational normal curves in PN, well, conics, and it will become clear why I write conics in P3 as embeddings of P1 times P1. And all classical embeddings we learn in the beginner's course of algebraic geometry, like Veronese, Segre, Plücker embeddings, many others. So today I will speak about an attempt to describe deformations of another embedding, which will be the embedding of full flag variety of so 1- and 2-dimensional subspaces in R3. This is the smallest parabolic homogeneous space where we have a non-trivial filtration on the tangent space. It will play an important role in my talk. So it's a contact manifold, 3-dimensional contact manifold. And we'll be embedding this manifold into P7, or in a very specific flag variety, which I'll speak again, which I'll define soon. The general theory of such embeddings and deformations, there are deformations which includes canonical moving frame and description of invariants for such embeddings was developed a few years and published a few years ago by our joint work with Mashida and Morimoto. So what motivates us to consider this one particular example? Surprisingly, we by looking at this example, by investigating, by looking at the variance of such embeddings, we see a lot of similarities with classical projective geometry of surfaces in P3. So when we speak about projective geometry of surfaces in P3, we mean something 2-dimensional, preferably with a non-degenerate second fundamental form that is embedded into P3. And this 2-dimensional manifold, if it's if a second fundamental form is of indefinite signature, signature 1,1, will carry families of asymptotic curves, 2 families of asymptotic curves, but other than that, it's just a 2-dimensional manifold without any special filtration of the tangent space. Here, in flag variety of subspaces in R3, is a contact manifold, and we'll be embedding contact three-dimensional manifolds into P7 for some reason. So we may think about as if we try to build a contact analog of projective geometry of surfaces. So we'd like our surfaces to become three-dimensional contact manifolds, and of course we cannot embed three-dimensional contact manifolds into P3, so we need to increase the dimension of our projective space, and why P7 we'll see in a second. So again, I repeat, there is a well-known classical approach how one can study projective geometry of surfaces, so surfaces in P3 via overdetermined systems of linear PDEs. One can think about U as a radius vector in affine coordinates, for example, in XYZ coordinates, and then rewrite write the equation of this radius vector. And if our surface, and this is a general assumption during the talk when I speak about projective surfaces in P3, I always assume that they will have a non-degenerate second fundamental form of signature 1, indefinite one. So then one can bring the equation on the radius vector to this particular form, where AIs, BIs, and CIs are certain functions of XY. XY are coordinates on our surface, and these are asymptotic coordinates in this case. On the other hand, so suppose somebody has given us this system of PDs, and we assume the system is compatible, which means that if we differentiate the first equation by y 2 times, that will be the same as if we differentiate the second one by x 2 times. So then the solution space of such system is exactly 4-dimensional, and this solution is uniquely determined by the 3 partial derivatives we have, which is u, ux, uy, and uxy at a single point. So it's a Frobenius type system. So it's certainly a system that's normally not very difficult to solve. Now, if we have this 4-dimensional solution space, we can turn the solution space into coordinates or projective coordinates for our embedding. So if U0, U1, U2, U3 is a basis of the solution space, then we just assume that U0, U1, U2, U3 are projective coordinates. And this gives us an embedding of something 2-dimensional because we have U is a function of x and y. So U0, U1, U2, U3 will be functions of x and y. And what we'll have is a surface in P3, y P3, because actually, of course, the basis is not unique. It's defined only up to linear transformations. And therefore, what we get is defined up to projective transformations. So we really speak about projective surfaces viewed up to projective transformations in P3. So necessarily, because we've chosen a very specific left-hand side of such system, so our system has a very specific symbol, we will get exactly what I call hyperbolic surfaces in P3. So it's a surface with non-degenerate second fundamental form of signature 1, and x and y will be x equal to constant and y equal to constant will be asymptotic curves. So x and y will be automatically asymptotic coordinates on such surface. And actually, one can think what happens. One can recover the most symmetric hyperbolic surfaces in P3 if one use trivial system with a given symbol. So if all right-hand side vanishes identically, then what we get is exactly the image of the Segre embedding. So it's written here in the affine coordinates, and it's another way to write I think hyperbolic paraboloid. That would that's what it would be called in the classical literature. So how do we turn this approach to projective geometry of surfaces? And I should say that it's very fertile approach used in classical, both in classical works. Just a second. So if I go back, so this approach to studying surfaces in P3 via systems of PDEs links 2 points of view, geometric and analytical PD system of view, PD point of view, the same object, and as a result, we have a nice description of projective invariants, like peak invariant, cubic form in terms of coefficients of the system. There are also interesting classes of such surfaces with some additional ansatz, so additional relations with the coefficients AI, BI, CI, and compatibility conditions then for such system result in many interesting classes, well-known classes of integrable PDEs. So actually, compatibility equations of such systems is a huge source of geometric source of integrable PDEs. So how do we contactify this point of view? And in terms of geometry, is not easy. In terms of PDEs, it's fairly easy. So what we do, we just replace partial derivatives in x and y by so instead of two-dimensional surfaces, we consider now three-dimensional manifolds, and replace partial derivatives x and dx, dy, which of course commute, by Lie derivatives along two vector fields x and y in a three-dimensional manifold. And now we assume that these two vector fields span a quantum distribution. So instead of instead of looking at the holonomic version, we look at the non-holonomic version of such system. So a bracket of x and y is a certain vector field z. So x, y, and z will form a frame on M, so linearly independent at each point. And then formally we rewrite the same system. So we have this the same system. Now, of course, we have plus one more coordinates. So u now a function of three variables, not two variables as before. And also coefficients AI, BI, CI also now functions of three coordinates, because they're all functions on M, which is three-dimensional. And but the system stays the same. So the very first question, and of course, to understand if such system is compatible or not is much more difficult work, because it's not just enough to differentiate first equation via vector field y 2 times, and second via vector field x 2 times, because y squared x squared is no longer equal to x squared y squared. So one has to differentiate it actually 4 times to get relations which have to be all satisfied. So compatibility equations turn out to be of order 4 in this case, not 2. But if we assume they're all satisfied, again, we end up with a finite dimensional solution space. It's probably not easy to immediately grasp what is the dimension of such solution space, but it turns out to be 8-dimensional. And so it's an easy exercise, so to say, in playing around with vector fields x and y and relations, and doing some computation, essentially in the universal enveloping algebra of Heisenberg-Lie algebra, three-dimensional Heisenberg-Lie algebra. But if this can be done all very naively, and then we see that each solution is uniquely determined by this initial data at the point. So you see, as before, it's u, xu, yu, xyu. But for example, if you compute yxu, then xyu minus y, xyu minus yx is z. So this is how zu appears here, and then x, z, y, z, and z squared have to be specified, and all other partial derivatives can be derived from these relations. So these 8 entities are can be chosen arbitrarily, again assuming we have all compatibility conditions satisfied. So we have 8-dimensional solution space in this case. And again, playing the same take. So we take a basis of the solution space, and we get our embedding of a three-dimensional contact manifold into P7, where U0, etc., U7 are homogeneous projective coordinates of our embedding. Functions, they all depend on three variables now. So each such system, if it's compatible, defines us an embedding of M, of contact manifold M into P7. So this is why I mentioned that we would be considering P7, submanifolds in P7 at the beginning of the talk. And of course, the question is what kind of embeddings we get this way. Certainly, these are not arbitrary embeddings, because again, we have very specific left-hand side of this equation, and it should somehow so we are not we cannot expect that we arrive at any embeddings of contact three-dimensional manifolds in the P7. There will be some special conditions for such embeddings. And second, even an easier question. So suppose we are just taking a trivial system as before. So suppose we take X and Y to be, for example, choose local coordinate system with some classical representation of the basis of contact manifold. One of your preferred choice, and I'll be giving some of those choices later. So for example, like this one, so X is dx plus Y dz and Y is dy. So it's the ones that resembles coordinate system on first jet space of maps from R to R, for example. And suppose we write a trivial system, and I'm sorry for the misprint. Of course, it should be X squared U equal to Y squared U equal to 0. What kind of embedding we get this way? So it should be the most symmetric one, and yes, it will be, but what is the geometry of such embedding? So what kind of geometric objects we deal with? So to understand even the trivial case, we need to do some Lie algebra. Well, not a very complicated one, but there will be a few slides of Lie algebra theory. Hope very elementary, but still there is some. So what we will need, we will be first of all dealing with graded Lie algebras. So on the next 2 or 3 slides, I'll deal with gradings of Lie algebras. Again, Lie algebras will be not very complicated. So our most complicated Lie algebra will be SL3. So there might be SL7 as well. SL8, sorry, in this talk, but nothing more complicated. We will have gradings on these Lie algebras. So it's a grading by Z, but of course, as all our Lie algebras will be finite dimensional, the grading will be symmetric in negative and positive directions and only finite in each of the directions. And you can imagine such grading of SL given by the distance from the diagonal, for example, where you count elements above the diagonal with degree plus and below the diagonal with degree minus. So then for each such Lie algebra, and we assume G is semi-simple, and again, as I say, so I don't want to deal with the general series semi-simple Lie algebras. So our examples, in the examples we will be dealing with, G will be just SLV, just OGL. Then if you take only a non-negative part of G, that's the same as taking, say, upper triangular matrices or block upper triangular matrices, and that's called parabolic subalgebra of G. So it's a classical definition. Then a quotient space, G by P, is what's called generalized flag variety. In our cases, it will be flag varieties of flags of certain dimension Rn. So it is actually, it has a structure of so-called filtered manifold. So it has a filtration of the tangent bundle, and this filtration is compatible. So a filtered manifold is a smooth manifold equipped with the filtration of a tangent bundle, such that this filtration is compatible with the Lie bracket. So if you take a vector field inside T minus I and the vector field inside T minus J, take a bracket, will end up inside T minus I minus J. So a very typical example is a contact manifold, where contact distribution defines you T minus 1, and then T minus 2 will be all tangent space. Again, I don't want to spend much time on these basics. What really is important, so if you take any fixed point on G, yes. So if you have now any submanifold inside such homogeneous space G mod P, we can define its symbol very easily. So we have a filtration of the tangent space on G mod P, and then tangent space at a point is a subspace here. So we just take associated graded space. And it turns out that if you take associated graded space to this initial filtration of tangent bundle of G mod P, that will be exactly model G minus at each point. G minus is what is left if you quotient G by P. So TXM, so a graded space associated with tangent space of M, is just a graded subspace in G minus. And this is what we call a symbol of a graded subalgebra in G minus. It's a symbol of submanifold M. So this is a very general theory that works for any parabolic homogeneous spaces or generalized Slack varieties and submanifolds there. We'll need just a small part of this theory, but this is a general definition of a symbol, and we'll use it in our case. So, yeah, as promised, so we'll specialize now to a very, very specific example of this general picture. So we'll have, first of all, let's look at SL3R. So 3 by 3 traceless matrices. It has this grading from -2 to 2, exactly defined by the distance from the diagonal. So elements of the diagonal have degree 0, and above the diagonal, right above the diagonal, have degree 1, and top right corner will have degree 2. And if you go down, it will be -1 and -2 respectively. So the dimensions of these gradings, so grading goes from -2 to 2, and the dimensions of G minus 2, G minus 1, G0, G1, G2 are exactly 1, 2, 2, 2, 1. And again, it's very easy to see that on the diagonal, for example, we have two-dimensional subalgebra. That's in GL3 it would be three-dimensional, but we killed trace, so it's two-dimensional. Above diagonals there are two elements, below the diagonals there are also two elements, and finally in the bottom left corner we have just one slot, and the top right corner we have only one slot. So this is the dimensions of all subspaces in this decomposition of G into the direct sum. So now take V to be the adjoint representation of G. So SL3 acts on itself via Lie bracket. So then V will be also eight-dimensional as G itself. But now we can equip SLV. So this dimensions can be viewed as dimensions of certain subspaces in V. So V and G are the same. But SLV, and we need SLV, so we need SL8R essentially. So 8 will also be equipped with a grading, but now it will be based on the block diagonal decomposition of R8 into blocks of dimensions exactly 1, 2, 2, 2, 1. So altogether it's 8. And similarly, it will have grading with degrees coming now from -4 to 4, because we have, for example, 5 blocks on the diagonal. So now, if you consider flags of these dimensions, so it's we can have a fixed flag in V. So fixed flag is defined as that one. So it's one-dimensional G2. Then G1 plus G2, it's 3. G0 plus G1 plus G2, it's 5. Then it's 7. We add also G2, and finally it's all G, so it's 3. So we need we would like to consider flags in R8 in 8-dimensional V, but of dimensions 1, 3, 5, 7. So this is kind of the embedding we would like to have. Well, this is the setup we'd like to have. Yes, so, and of course, G itself, so SL3 is embedded now in the SLV. So SLV is 63 dimensional, so it's 8 by 8 minus 1. This 8-dimensional G is embedded into SLV. And G minus also becomes a negative part, lies as a gradient subalgebra. It's a negative part of SLV. But the dimensions like G minus is 3-dimensional, but SLV minus is, well, it's difficult to compute. So it's you have to work to compute what is SLV minus essentially by subtracting from 63 dimensions what we have on the diagonal divided by 2. So it's on the diagonal we have 1, 2, 3, 4, 5 blocks, 1 by 1, 2 by 2, 2 by 2, 2 by 2, 1 by 1. So it's 14, but minus 3 is 13, 63 minus 13 is 50, so and then divided by 2. So SLV minus is 25 dimensional. So this 3-dimensional G minus will sit in 25-dimensional SLV. So essentially, what we'll be interested in, and we'll be interested in 3-dimensional submanifolds in this huge flag variety, which has exactly the symbol G minus in the above definition. So it's not easy to understand what this means, but we'll have a different geometric interpretation of this thing. Yet we would like we need this general definition to understand what exactly to be precise in defining in characterizing the embeddings we get from our non-holonomic system of PDEs. So we consider such embeddings, so 3-dimensional manifolds in this huge flag variety with this symbol, G minus, as embeddings of SL3 type. So let's understand what it is actually. So first of all, any such submanifold, 3-dimensional submanifold of type SL3 is a 3-dimensional contact manifold, because in particular its symbol is the same as G minus, and G minus is 3-dimensional Heisenberg-Lie algebra. So M will be necessarily a contact distribution, a contact manifold, where T minus 1 M denotes contact distribution. Next, we can, if you look at this big flag variety, we can forget about all other subspaces except the first one. So it has very, it has a natural projection to projective space associated with V. So if you forget 3, 5, and 7-dimensional spaces and keep only 1-dimensional, that gives us the embedding or the projection to P7. So any such submanifold M that sits in this flag 1, 2, 3, 5, 7 and has our predefined symbol can also be viewed as a projected to P7, so it will be an embedding to P7. So it's already better. So we would like to, we see that we need to deal with certain 3-dimensional submanifolds sitting in P7. Next, I skip algebraic reasoning here, but what we can have, so suppose we are given any 3-dimensional manifold in P7 and manifold equipped with a contact structure, then we can build a an osculating flag. So essentially, in classical projective geometry, we would start taking tangent space, second tangent space, etc. Here we do something similar, but when we have a tangent space, we differentiate only along. We osculate only the contact directions, along the contact directions. So we define minus first oscillating space to be an affine space associated with the point x itself. So it's a line in V. Then iteratively, we will define a sequence of osculating spaces by differentiating what we've got so far, but only via contact directions. Not all directions inside them, but only via contact directions. So it will be like a weak osculating flag. And it turns out that in this case, so if we started from M in flag variety 13573, and we fixed a symbol of this embedding, and then projected that back to P7, then actually the complete embedding, all embedding from M to flag variety can be reconstructed from just embedding of M to P7 via this as weak oscillating flag. So it's actually such things are one-to-one. And then we say that a three-dimensional contact manifold or embedding of M into P7 is also of type SL3 if it first of all has the right dimensions of this weak oscillating flag. So I want this X to be one-dimensional, then something is three-dimensional, then five-dimensional, and seven-dimensional, and then we get all V finally via this sequence of oscillating flags. So we say that a contact manifold M embedded into P7 is of type SL3 if it lifts exactly to the submanifolds M in flag variety with the prescribed symbol G minus and SL8R minus. So it's probably a long definition, and it hides a lot of algebraic complexity and details here. The main message here is that we would be looking for to characterize the embeddings of contact manifolds into P7, which we get from this non-holonomic system of PDEs, we really need to consider this weak oscillating flag, and this dimensions of this subspace should be like here 1, 3, 5, 7. And there are additional algebraic relations coming from this prescribed symbol, but we can skip them for now. So let us instead understand what corresponds to the flat example, flat system. So if we have x squared u equal to y squared u equal to 0, where x and y are two contact vector fields, we actually arrive at a very well-known rational homogeneous variety for embedding of the following type. So let's look at what's called highest root orbit in PV. So SL3, the group SL3, acts the joint representation. I recall that V is Lie algebra SL3 viewed as a joint representation of SL3. So you consider what is called the joint variety, but actually there is a much easier way to describe it. So we just look at all 3x3 matrices conjugate to this highest root space, and highest root space in this case is just this one-dimensional subspace in the 3x3 matrices. So what is the space of all matrices conjugate to this one? Or we view them in the projectivization of SL3, so we view them up to multiplication as well. So we of course end up with the set of all trace-free rank 1 3x3 matrices. So it's clear that if you conjugate this matrix, it still is rank 1, it's still trace-free, and actually any rank 1 trace-free matrix is conjugate to this one up to a scale. So So this adjoint variety, or complicated word, is nothing but just rank one trace-free matrices, 3x3 matrices. We actually can identify this space with a full flag variety of subspaces in R3. So how do we do that? So actually, and how do we do that? So each rank one matrix, 3x3 matrix, can be written as a tensor product of a covector alpha and the vector v, and the conditions that it's trace-free says that the pairing of alpha and v should be 0. And I say that up to a constant, if you consider such tensor products, they in one-to-one correspondence with flags. And this is the flags. So one-dimensional subspace is given by V, two-dimensional subspace is given as a kernel of alpha. And because we have this trivial pairing, so alpha V is 0, we clearly alpha perpendicular contains V. And vice versa. So any such flag can be written, can uniquely be described by such rank one trace-free matrix up to a scale. So actually, this adjoint variety is nothing but a full flag variety in R3, and it carries a natural context structure. Again, there is an easy way to describe it geometrically, because if you fix V and vary alpha, you get one direction in the tangent space, and you fix alpha and vary V, you get another direction, and these two directions together give you contact distribution on this flag variety. And so it's, first of all, so it's a three-dimensional contact manifold, and on top, it's naturally embedded into P7, where P7 is our PV. So that's, again, one of those rational homogeneous varieties. So a general theory says that if you have such embedding, we actually know how to build a moving frame or how to find invariance of such embedding. I'm skipping this. So this is an earlier result with Mashida and Morimoto. So we can have a canonical reduction of a principal bundle over P7, and this reduction has very nice properties, which I probably skip now. So most importantly, that our Markov form, which exists on which is a cell V valued one form over.
Yeah. I'm sorry. Is it a typo or item one? B equals ST or SL? What is ST?
It's ST, yes. ST is an upper triangular trace, upper triangular matrices with determinant one. So it's T, okay. T, so it's special triangular 3x3 matrices.
Special triangular, okay, thank you.
So this is a stabilizer of this principal bundle we construct. Again, I don't want to look into the detail, and I'll give references later on for those who are interested. Most importantly, that this theorem sorts out, gives us full understanding of what are the local differential invariants of such embeddings, and also it allows us to characterize those embeddings which are locally equivalent to our embedding of like flat, what we call flat embedding of flag 1, 2, 3, 1, 2 of full flags in R3 into trace-free 3x3 matrices. So there is also a certain nice application of this general theory that we know where to find what I call fundamental invariants. These are all local differential invariants of the embeddings. Fundamental invariants are the ones which control flatness, if you like. In classical projective geometry surfaces, this would be cubic form, actually. A certain tensorial object that vanishes if and only if our submanifold is locally equivalent to the most symmetric one. So there is a cohomology theory, and probably I skip this because it's very nice. Most importantly, that in this case, this cohomology can be computed very explicitly using pretty deep algebraic techniques called Coston's theorem, and we find out that there are exactly two functions, two fundamental invariants that control whether our embedding of such a SL3 type is equivalent to the adjoint variety, locally equivalent to the adjoint SL3 variety or not. So it's out of this huge dimensions. So we have three-dimensional contact manifold. We embed it into P7. So it looks like we have a lot of data and a lot of functions. Actually, there are just two scalar functions that control whether our embedding is flat or not. So yeah, that's what I say. So now I come to the last part of my talk. So this was just I gave you an overview how one can relate certain geometric objects, namely embeddings of certain type of contact manifolds, with our contact analog, or like with our system of PDEs given by two vector fields x and y on the contact manifold. So now we wanted to do some classification. So we wanted to find explicit examples of such things, and maybe that would help us to understand what are different phenomena that we can expect when we study such things. So we'd like to. So we studied. We did a very typical question when one deals with such objects is to classify those which are most symmetric, and we have exactly one embedding which has a very large symmetry algebra, which is our flat one. But we also have many embeddings which have transitive symmetry algebra. So to give you precise definition, so if you have such embedding, and we'll mainly speak now about embeddings of M into P7. A-tiled, yeah, I see the question. What is an A-tiled is the first theorem? I have to go back. Probably this one. Yes, so A-tiled is a so P is a principal frame boundary over M. So this is the reduction of this is what we normally call moving frame. So it's not a unique frame; it's actually a bundle of all such frames. And A-tiled is just a fundamental vector field of this principal bundles that corresponds to the corresponding element in the Lie algebra. So it's
Thank you.
So, yeah. I probably skipped too many details here. Sorry, but it would take probably a lot of time for me. Okay, so the objects we would like to classify are the following. So we look for the scalarity embeddings or embeddings of M into P7 with the prescribed dimensions or prescribed symbol, which include in particular prescribed dimensions of the Vico scalarity flag. And on this flag variety, as well as on P7, we have a natural action of SL8 on projective transformations. So symmetry algebra of M is defined as all vector fields from SL8, which are tangent to M. And we say that those flows preserve M. It's natural infinitesimal definition of a symmetry. And we say that M is locally transitive, the symmetry algebra is transitive on M. That is, if restricted on M, it spans all Tm. So in particular, symmetry algebra of M, yes, and we are interested in, so we would like to describe all such embeddings of a cell-3 type with transitive symmetry algebra. In particular, symmetry algebra should be at least 3-dimensional in this case. To be transitive on contact manifold. So there is, if you assume this transitivity on that, then we actually can interpret our systems. We can simplify the conditions on the corresponding system of PDEs we consider. So we can really think about the system written in terms of two vector fields. Here I change the notation of xy to z1 and z2. So we can assume that z1 and z2 are certain left invariant vector fields on a 3-dimensional Lie group H, such that z1, z2 is a left invariant contact distribution on H. So we still want the z1, z2 to be non-holonomic. So they span a contact distribution, but now we can assume that we have certain 3-dimensional transitive, simply transitive action symmetry algebra, and then the same symmetry algebra will be present for the corresponding system of PDEs. So Z1 and Z2 are left invariant vector fields. They span contact distribution, and we now can assume that all coefficients are constants. And still, it's highly non-trivial question when such systems are compatible. So in case of if Z1 and Z2 were commuting, then that would be a trivial question, but Z1 and Z2 still non-commute, even if they are left invariant vector fields on the Lie group. So to classify all such systems requires a lot of work. And here's the final result. So this is a complete list of all such systems. Surprisingly, there are very few of them. So even if you are dealing with very huge dimensions, there are very few embeddings with locally transitive symmetry algebra. In particular, we have exactly one so-called flat example that has 8-dimensional symmetry algebra, so it's maximal possible symmetry algebra actually for such embeddings. Then we have exactly one of them, so it's almost trivial, but it has just some right-hand side appearing here, 6z1u. Again, 6 is a technical coefficient, so it can be actually any in this case. And that's a unique example with a 4-dimensional solvable symmetry algebra, 4-dimensional symmetry algebra which turns out to be solvable in this case. And this is what we call submaximal. And we have a number of examples which have exactly simply transitive symmetry, which is 3-dimensional, either solvable or isomorphic to SL2. And these are all explicit equations where P1 and P2 are parameters, constants, and sometimes they satisfy some additional relations, like here, for example. So actually, there is at most one parameter, 3-parameter present in such systems. And again, just to give you an idea what kind of examples these are, we considered two of them in more detail. The one which is submaximal, and the other one which has exactly 3-dimensional symmetry algebra, which is a SL2R. And the first one turns out to be exactly the contact analog of what's known as Cayley's ruled cubic. So Cayley's ruled cubic is a very famous surface in P3, which was present in the original manuscript. So probably not many people know that. Well, many people know that if you take a smooth algebraic, smooth cubic surface in P3, our complex numbers, then there are exactly 27 lines on the surface. But actually, smooth means no singularities, and there is also a question. What is osculating? Yeah, osculating, we use term osculating for the embedding. So sorry for going back to the questions, but probably it makes sense. Yes. So we say that such embedding is well, actually, oscillating embedding of SL3 type, if the oscillating spaces of such embedding result in the embedding of M3 into flag variety of dimensions 1, 3, 5, 7. So it's oscillating spaces have to be exactly of the right dimensions. Probably it's not the most correct terminology here, but oscillating means that oscillating subspaces have to be of type SL3, and the symbol also has to be of type SL3 if you consider this as an embedding into the flag variety flags of dimensions 1, 3, 5, 7 in array.
Thank you.
Mm-hmm. Yeah, so back to Cayley's root cubic. So non-singular cubic surfaces in P3 are a very classical topic in algebraic geometry, but it's less known that Cayley was able to classify all cubic surfaces in P3, including all singular ones. And among them, there is this nice one, which is called Cayley's root cubic, which actually possesses infinite number, one parameter family of lines. It's clear that if x is constant, we get a line on the surface. And it turns out that it corresponds to this very nice second order system of PDEs. Ux is equal to uy and uy equal to 0. So if you solve this system, we get four-dimensional solution space. And if you interpret this four-dimensional solution space as projective coordinates of certain embeddings, that's exactly this Cayley's cubic, root cubic. It's also known to be a submaximal surface among all hyperbolic ones in P3. So submaximal means with the submaximal dimension of a symmetry algebra. So the most symmetric is paraboloid, hyperbolic paraboloid, and this is, it possesses six-dimensional symmetry. And this one is the next one. It possesses only three symmetries, and all other surfaces, hyperbolic surfaces in P3, have at most two symmetries. So what we do, we just mimic what we've done before, namely we take x and y to be non-commuting vector fields from RC with a standard representation, standard contact coordinates for one of the standard ways to write contact coordinates from RC, and consider the system. And we get a certain interesting embedding, which is exactly, it has a four-dimensional symmetry, and that's also a unique submaximal embedding of our SL3 type. It can be written very explicitly, but it requires, it cannot be written via a single algebraic equation. Unfortunately, it's still algebraic. And it possesses some, well, it also actually possesses one parameter family of straight lines ruling. So it's ruled by straight lines, which are on top of this contact lines. So they're tangent to the contact distribution or not. So there is a lot of similarity in the, between this classical Cayley's root cubic and the embedding, which is defined by this system of PDEs, non-holonomic version. Yeah, so I mentioned a few properties which makes them really similar, like one-dimensional, unique submaximal models, and both have transitive symmetries with one-dimensional stabilizer. So a last example, and I'll probably finish then, is the example where we have an embedding with the symmetry, simple symmetry algebra SL2, and again, we can write it very explicitly in terms of left invariant fields on SL2. So if you take x and y to be two vector fields which correspond to this upper and lower triangular, strictly upper and lower standard basis in SL2, then of course x, y spans a contact, left invariant contact distribution on SL2. And we can consider the system. So x squared u is minus alpha, well, alpha proportional to yu and y squared u is proportional to xu, where alpha beta are non-zero. It turns out that it's compatible if and only if alpha beta is 10 for some reason. So this is a typical compatibility condition for such systems. And there is also a natural equivalence relation here, so you can scale alpha by t and then divide beta by t as well. So to have everything nicely written and symmetrically, we can normalize both alpha and beta to square root of 10. Seems to be the most natural normalization. And then the system possesses also, so it's a compatible system. It has exactly 8-dimensional solution space and gives us the embedding with a simply transitive symmetry algebra SL2. Actually, it can be written very explicitly in coordinates as well. So we can choose a local coordinate system XYZ on the SL2. So it's a carefully chosen system in which left invariant vector fields look like this. So it's chosen such that you can swap X and Y, and it's kind of a swapping of Z1 and Z2. Then you can imagine actually, so if Z1 and Z2 are these vector fields, and that's one of the simplest coordinate representations of left invariant quantity distribution on SL2. So if one can then expand the system very explicitly in coordinates, in X, Y, Z coordinates, the resulting system would look extremely ugly. So it's really essential that it's written in terms of left invariant vector fields and this nice form. Then to solve such system, one has, because Z1, Z2, Z0 are left invariant vector fields, they commute with right invariant vector fields. Right invariant vector fields are this ones in this case, so exponential shows up. And of course, this right invariant vector fields will be symmetries of our equation, so therefore they will preserve solution space, and then one can explicitly write the solution space like that one. So it has solution space is spanned by constants, or function, constant function is the solution of our equation because we differentiate at least once. But then other 7, so we have in total 8-dimensional solution space, so we need to have 7 other independent solutions. They can be explicitly written down in this pretty ugly form, or beautiful form if you like. So you choose this solution and then start differentiating it along Z2 prime, and then it generates you after 7 times, differentiating 7 times, you get 0. So it actually is kind of harmonic theory in SL2. It is actually harmonic theory in SL2. You find explicit form of the solution space for such system. So this is to demonstrate what kind of equations and systems and embeddings one gets if we consider such fairly innocently looking systems of PDEs. So my slides have references, and well, actually I have to update the last one because it did appear on archive already. So I will probably update the slide and send this for putting it on the website. To finish, there's still one more missing objective in the talk. We'd like to understand what kind of integrable PDEs show up here if we think about, if you write explicitly compatibility conditions for some systems. That's research in progress. Okay. So I stop here. Sorry if it was a bit more than expected in time.
Yeah, okay. Thanks a lot. Questions, remarks? Well, there were some questions during the talk. No more questions. Okay, Boris, thanks a lot. It was interesting, and you are always welcome to
Thank you very much.
give a talk here. And thanks for to everyone for participating. And our next meeting will be in a week, and we will listen to a talk by Maxim Pavlov. So goodbye, have a nice week, and see you in a week. Goodbye.
Thank you.
Всего хорошего.
До свидания.